Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 5 in our Circuits 2 lecture series where we talk about, or where I talk about the discharge of an RC circuit. And so in our previous module, we presented a circuit where we had a resistor in series with a capacitor. And when we switched in a voltage source, we saw how the voltage across the capacitor increased slowly as a function of time. Now we're going to take a look at what happens when we take that same circuit and we switch the source out and let the capacitor discharge back through the resistor. So here's the circuit that we're going to be analyzing. And if you remember, in our previous module, the switch was switched over here to ground, and then at some time t0, we flipped the switch over so that our voltage source was applied across our circuit. And gradually, the voltage across the capacitor, which we refer to as V0 of t, started out at 0 and then asymptotically grew to be equal to Vs. And so what we're going to assume is that when we flip this switch back to ground, enough time has passed for the voltage across the capacitor to reach the steady state solution. And so if we were to write that down, basically we're assuming that the time t1 is much greater than the time t0. And t0 in our previous module was when we flipped the voltage supply in to apply the voltage across our circuit, so that we assume that the output voltage at time t1 is equal to our steady state solution Vs. And so once we flip the switch, what's going to happen is the positive voltage across our capacitor is going to cause a current to flow through the resistor in this direction from right to left. And what we want to do is we want to figure out how this affects the voltage across the capacitor as it discharges through the resistor. This is sometimes known as the source-free response, because basically we're looking at how the capacitor voltage behaves once we remove the source from the circuit. So if Module 4 was where we determined the step response of the circuit, this Module 5 is where we're determining what's known as the source-free response for the circuit. So just to be specific about that, the source-free response determines what happens to our output voltage, V0 of t, for the time values greater than or equal to t1. Again, where t1 is where we switch out our source. And so, similar to how we approached the step response, we're going to determine the differential equation that governs the source-free response, and we're going to solve it to get the solution for V0 of t. And so we start the same way that we did before, using Kirchhoff's current law. And for this analysis, I'm still going to define the direction of current through the capacitor as from the top to the bottom. Just it helps our analysis a little bit. So we have negative IC is equal to IR. And then I'm going to substitute in the equations for the current through a capacitor and the current through a resistor. For now, I'm going to drop the notation where I'm showing V0 as a function of time, just to sort of simplify our notation a little bit. And then I'm going to move terms around a little. And we're going to have dV0 over V0 is equal to negative dt over RC. And if you compare this with your notes from the previous module, you'll notice that the right-hand side of the equation is exactly the same as it was for the step response, but the left-hand side of the equation is a little bit different. But we're going to use exactly the same approach to solving this differential equation. We're going to integrate both sides of it, basically. And we're going to integrate the voltage from the voltage at time t1, which is equal to Vs, up to whatever voltage we have at time t. Again, remembering that t is sometime greater than or equal to t1. So this equation is only valid for times greater than or equal to t1. dV naught over V naught is equal to the integral from our switching time to our current time t minus 1 over RC. This time I'm going to use d tau. Like I said in module 4, I used the same variable t of integration and the limit here, but I really shouldn't have. I should have used a different variable here, so I'm going to fix that in this module. And using a very similar approach to how we solve the integral for module 4, the solution for these two integrals is the natural log of V naught at times t minus the natural log of Vs. That comes from the lower bound of our voltage integral, is equal to minus t minus t1 over RC. Exactly the same as module 4, except now we've got t1 instead of t naught. Using our property of logarithms, exactly like we did in module 4, we can write this as the natural log of V naught at time t divided by Vs is equal to minus t minus t1 over RC. Taking the exponent of both sides, gives us the exponent of the natural log of V naught at times t divided by Vs is equal to the exponent of minus t1 over RC. This exponent and the natural log cancel out, so we can write V naught of t over Vs is equal to e to the minus t1 over RC. Or in other words, the voltage across our capacitor after we switch out the voltage source is equal to the voltage source value Vs multiplied by this decaying exponential. And just like, or similar to, our step response in module 4, this is the transient term, or the transient solution to our response. And you might say, well, where's the steady state response in this case? The steady state response is actually a voltage value of 0. Because when we switch out our voltage source and we allow the capacitor to discharge through our resistor, that voltage across the capacitor is basically going to decay down to 0. So it's going to discharge all of the charged particles it's stored up through the resistor until there's no more charged particles. Then we know that the voltage across the capacitor is proportional to its charge. So if it's depleted its charge, then it makes sense that its voltage should be 0. And again, remember that this equation is only valid for time values greater than or equal to T1, which is where we switched out our voltage source. Okay, now we're at a point where we can take maybe a little bit of a detour or diversion and talk about an application of some of the stuff we've learned about so far. And the application I'm interested in talking about is supercapacitor batteries. And so we know that a capacitor stores energy. And that energy is equal to 1/2 times the capacitance times the square of the voltage across that capacitance. And we saw just now in our source-free scenario that if we charge up our capacitor and then we switch it across a resistor that is connected to ground, essentially what happens is that capacitor discharges into the resistor, runs some current through the resistor. And so this allows us to think of a capacitor as potentially a substitute for a battery, right? Because you could charge up your capacitor just like you charge up a battery, and then you connect it to some kind of load that you want to drive, which we could model as a resistor connected to ground. And for a while, current will flow through that load, and then it will do some useful work for us. And now we've got the theory that will allow us to determine how long that voltage is sustained across our load and how long potentially this battery capacitor could be powering whatever we want to use. So we could imagine this as maybe being a cell phone or perhaps even an electric car. And it's the electric car example that I kind of want to go a little bit further with. And so if we think about our electric car example, we would want to, and if we want to propose a capacitor battery as an alternative to a gasoline engine, let's say, a capacitor battery powering an electric motor as an alternative to a gasoline engine, then we're going to need, in order to be competitive with gasoline-powered cars, we're going to need to store roughly the same amount of energy in our capacitor that is stored in a typical tank of gas on a car. And so if we take a 45-liter gas tank is kind of a typical car gas tank size. So the amount of energy we have in a gas tank is equal to 45 liters times 77 kilograms of fuel per liter. And then the energy density of gasoline is roughly 45, oops, that's not millijoules, it should be megajoules per kilogram. Right? And so our liter units cancel, our kilogram units cancel, and the result is 1,559 megajoules of energy. Now, let's figure out how big our capacitor would have to be, how many farads our capacitor would have to be in order to store a similar amount of energy. So let's assume a voltage of 300 volts. Which is a typical value for an electric car. And let's substitute in 1,559 megajoules and 300 volts and solve for the value of C, our capacitance. And so it would be equal to 2 times 159 megajoules, 1,559 megajoules divided by 300 volts squared. And so that gives us 34,650 farads. So the question, I guess, now is 34,000 farads big for a capacitor? And the answer is, yeah, it's really, really big. So just to sort of illustrate this, let's calculate the capacitance of the whole Earth. And what do I mean by that? Well, let's assume that we can make a capacitor where one of the plates is basically the surface of the Earth. So we've got this massive plate, this enormous plate, and we spread our charge across the surface of the Earth. So it's a sphere, basically. So we spread our charge across the sphere as kind of the outer plate of the capacitor. And then the inner plate is basically a single point in the center of the Earth. So it's this is kind of a contrived example, of course, right? But imagine, you've got a very small plate in the middle of the Earth and then a hugely enormous plate that covers the entire spherical surface of the Earth on the Earth's surface. And if you make this assumption, the equation for capacitance is equal to 4 times pi times the permittivity of Earth times the radius of the Earth. And so the radius is equal to 6,400 kilometers. The permittivity of Earth is equal to roughly 7 times E naught. E naught is equal to 8.854 times 10 to the minus 12 farads per meter. And so if you substitute these values into our equation, we get 0.712 millifarads. So we need 34,000 farads. And if we made a capacitor the size of the Earth, we would only get 0.712 millifarads. So clearly this seems like an impossible problem, and yet it's not. So researchers today are reporting what we're referring to, justifiably as supercapacitors that have capacitance values of up to 20 farads per centimeter squared. And this is an enormous value. And so you could ask yourself, well, if we made a capacitor the size of the Earth, and generally the bigger your capacitor is, the more charge it holds, how is it possible to make such supercapacitors that are so small? And the answer is basically this dielectric material, right? So the dielectric material of the Earth is not a particularly good dielectric for the purposes of this supercapacitance example. And so it's all about creating better and better dielectrics, essentially. So supercapacitors are approximately equal to, let's say, 20 farads per centimeter squared. And these are totally research values as of 2018, I guess. But if you find yourself at the start of your career, if you're, let's say, an undergraduate student, then, certainly over the 30 years that you're going to be working, you'll see this research make its transition into practice, I'm sure. And so if we wanted to figure out how big we needed to make our capacitor in order to get our 34,000 farads, let's say we've got, we just want to use a square capacitor, and the length of each side is equal to D. Then the value of D is equal to 34,650 farads divided by 20 farads per centimeter squared. And the answer is 42 centimeters. And this 42 centimeters, half a meter, certainly if you can roll the capacitor up, it's already on the order of a size that could actually fit into a car or a vehicle. And so we can see, based on this example, that supercapacitor batteries for vehicular applications, still very much a forward-looking research problem, but we're starting to get into the neighborhood where we could see these things actually being a commercial application sometime, hopefully in the near future.